This video continues our learning on scalars and vectors. We previously learned about scalars and vectors. We learned that a scalar was a quantity, some amount of something. A scalar does not have a direction. An example of scalar is distance, like how many miles your car says you've traveled when you make a trip. Or mass, which is a measure of how much matter an object contains. A vector has two parts to it. Like a scalar, a vector is a quantity, but a vector also has a direction associated with it. If you're going to the Square One Mall, you need to travel 3 miles on Route 1, but if you travel 3 miles south, you definitely won't get there. So the direction is important. Vectors can be represented by arrows. An arrow is a good model for a vector. The direction the arrow points shows the direction of the vector. But arrows can also have different lengths. So the length of the arrow represents the scalar portion of the vector, the quantity. A vector representing a car traveling 5 meters per second to the right would be half as long as a vector representing a car traveling 10 meters per second to the left. They would also point in the opposite direction. Using arrows to represent vectors also makes it easier to add vectors. You always add vectors tip to tail. That means you start the second vector where the first one ends, or you put the tail of the second vector at the tip of the first vector. The sum of the vectors is a new vector that starts at the tail of the first vector, where you started, and extends to the tip of the second vector, where you ended up. Say I wanted to add a vector of 5 to the right with a vector of 15 to the right. Now, a nice thing about vectors is that you can move them and it doesn't change the vector. So we'll move the 15, the tail of the 15, to the tip of the 5. And our new vector goes from the beginning of the 5 vector to the end of the 15 vector, like so. Now, to make it easier to see, we can move that one down. And we know that 5 to the right plus 15 to the right equals 20 to the right. That vector, 20 to the right, that's known as the resultant vector. The resultant vector is the vector that represents the sum of two or more vectors. Take some time now to try adding 3 up plus 7 up. Pause the video and in your notebook, see if you can add those two vectors. Pause the video now. Okay, if you put the tail of one vector to the tip of the other vector, you should get 10 up. Let's try another. 4 to the right plus 6 to the left. I didn't draw your vectors here, so you're going to have to do it yourself. Add a vector of 4 to the right plus 6 to the left. If you look at the two vectors, it gets a little bit tricky when you try to go tip to tail. Remember, the tail of the 6 goes to the tip of the 4. It ends up looking something like this with the resultant vector of 2 to the left. That resultant vector starts from the tail of the 4 vector, where you started, to the tip of the 6 vector, where you ended up. Now let's look at speed and velocity. Speed is a scalar. All speed is how fast something is moving. Velocity, however, is a vector. So you have the scalar portion of that, how fast the object is going, but also the direction. So let's look at this car going to go down the windy road, and it's going to stay at a constant speed of 35 meters per second, which means its speed is always 35 meters per second. The speed doesn't change, but as the car takes turns, its velocity will change. The velocity is always going to be in the direction the car is going. Now, this arrow, the length, represents 35 meters per second. The direction the arrow is pointing is the direction of the velocity at any given time. Let's check it out. awesome. That beats fast 5. So, as the direction changes of the car, so does the velocity. The speed always stays the same, but the velocity vector changes because the direction changes. Well, that's it for this video. Hopefully you've learned a little bit more about scalars and vectors and seen the difference between speed and velocity. Thank you.